Now, as we know, light travels as a wave. We said this in our general introduction right at the start. So if light travels as a wave, we can draw reflection and refraction diagrams showing the wave fronts as below. So if we draw a surface for the mirror, and we can draw a general, this arrow shows the general direction. Now this won't be accurate because I'm not using a protractor. So this is our general direction, but we know that the wave fronts are perpendicular to the direction of travel of the wave. Now when you show these wavefront diagrams, we show the direction of travel with our arrows. The wavefronts are at right angles to the direction of travel, and they should be approximately the same distance apart. And when they're reflected, they're still the same distance apart. Let's just remind ourselves the distance between the wavefronts is the wavelength. And this is our mirror surface, or our reflecting surface. So we find that whenever the light rays come in as waves, they are reflected. The angle of incidence and angle of reflection are the same, and the wave fronts are all the same distance apart on both rays. Now when we draw the wavefront diagram for refraction, we can see a different diagram. Initially, the direction of travel is shown by the arrow, and the ray is refracted towards the normal, and then as it leaves the block it's refracted away from the normal again. And this is a glass block. What we find in this case is that the wave fronts are the same distance apart on the incident direction of travel as they are in the emergent. So these two sections are the same. However, when the wave is travelling through the glass, we find that the wave fronts are closer together. This is also shown in the Waves and Sound video cast, so you can also refer to it there. So we find that the ray comes in, the light comes in, it slows down as we talked about earlier, and the wave fronts become closer together, and then it bends again away from the normal and speeds up as it leaves the glass and goes into the air. This means that during refraction some of the properties have changed. In reflection they're the same, but in refraction some of the properties have changed as follows. As we enter the optically denser medium such as glass, perspex or water, the speed slows down because it's optically more dense, therefore it's more difficult to travel through, so the speed slows down. The wavelength also changes. As we showed in the previous diagram, the wavelength decreases as the wave fronts are closer together. The frequency then. The frequency of the light is determined by the source, and because the source hasn't changed, the light is still travelling from the source even though it passes through a glass block and back out again. The source hasn't changed, so the frequency is unchanged. Those are important factors for refraction, and you should learn those. The speed of the light slows down, and the wavelength decreases, and the frequency is unchanged. And if you have any concerns about learning this, we can also use the wave equation to make sense of it. Phi equals lambda f. If the speed is slowing down, as it must do because the medium is more dense, therefore it's more difficult to travel through, it slows down, then the wavelength or the frequency must also change because they're in direct proportion to the speed. The frequency is associated with the source of the light. It hasn't changed, therefore the frequency is constant. So if the speed slows or decreases, then the wavelength